In a standard continuous integration pipeline, the delivery process feels entirely under your control. Source code is written, reviewed, tested, and flows predictably into a production server rack. But that localized control is an illusion. Deep within your dependency tree, an automated update triggers. A third-party library your application relies on has been compromised upstream, and it silently pulls malicious code directly into your build environment. This chart tracks the resulting fallout. By 2025, over 99% of all identified open-source malware occurred on NPM. At the same time, the share of breaches involving third-party components jumped by 30%. Relying on static compliance checklists to catch these insertions does not work. Securing this pipeline requires a strict engineering discipline that enforces cryptographic trust across 5 specific stages of delivery. The first stage is the foundation. Every container image you build directly inherits the complete security posture and any underlying vulnerabilities of its chosen base image. When a Docker file points to a tag like latest, unseen upstream updates flow silently into your builds, altering your foundation. The solution is digest pinning. Replacing the tag with a SHA-256 digest locks the components in place, and your pipeline rejects unverified changes. You combine this lock with minimal base images. By stripping binaries for shells and package managers from the container, you eliminate the tools attackers rely on to execute malicious code in production. Digest pinning and minimal images work together to cryptographically lock the pipeline's entry point. You mathematically eliminate upstream drift before compilation even begins. With the source material secured, the target moves geographically. The focus shifts from the code repository to the continuous integration build server. The pipeline now faces a structural problem. Even if the incoming source code and base image are perfectly verified, how do you prove the build runner itself wasn't compromised while compiling the artifact? You prove it with build provenance. This diagram maps the cryptographic evidence answering 3 questions. What source commit was used? What build configuration was applied? And what system performed the compilation? Pipelines must generate SLSA Level 3 attestations, permanently binding this metadata to the container. This requires ephemeral, isolated build environments. Each compilation job must run in a fresh, temporary context, so no residual state or hidden secrets leak between builds. Enforcing SLSA provenance provides a structural guarantee. An attacker cannot secretly inject malicious code during compilation without instantly breaking the cryptographic signature. The newly signed provenance-verified container artifact now exits the CI runner and routes toward your central container registry. Here, many teams generate a single software bill of materials at release time. It provides 0 operational security value. To be effective, an SBOM must be generated continuously at every single build. It has to be attached directly to the image alongside the provenance attestations. But standard continuous scanning flags hundreds of theoretical vulnerabilities based on library presence alone, generating paralyzing alert fatigue. To filter the noise, you apply VEX data. It cross-references the SBOM to determine if a vulnerability is actually reachable in the context of your specific image. Pairing continuous SBOM generation with VEX exploitability data turns a noisy, ignored document into a precise, real-time security gate for developers. We reach the final barrier in the delivery lifecycle. This is the strict boundary separating the container registry from your live production infrastructure. At this boundary sits the admission controller. It acts as an uncompromising gatekeeper, evaluating image pull policies before any execution is permitted. This admission controller must mathematically verify the SLSA attestation signatures. If the image lacks the exact cryptographic proof linking it to a vetted build process, the deployment is blocked. This boundary only holds if you apply least privilege across the pipeline. CI tokens must be tightly scoped so that a compromised build service account lacks the permissions to push directly to production. With strict registry access controls and signature enforcement in place, your production environment will reject any artifact that lacks an unbroken chain of provenance. The verified container clears the admission controller and enters production. It begins operating, emitting a steady, rhythmic operational heartbeat. At this stage, we must account for the inherent limits of pre-deployment analysis. Static scans cannot detect zero-day exploits or logic bombs designed to trigger only under highly specific runtime conditions. You bridge that gap with behavioral baselining. The system must profile the container's normal operational activity so it can instantly recognize when a process deviates from the established norm. The system watches for specific anomalies: an unauthorized outbound network connection, an unexpected child process execution, or writing to an immutable file system. Active runtime monitoring serves as the final layer of detection, identifying and isolating the sophisticated, latent compromises that successfully spoofed your static pipeline checks. We can now view the architecture as a whole. The process flows from trusted base images to verified build provenance, through actionable SBOM analysis, past strict policy enforcement, and into monitored runtime. Rather than simply stacking disconnected security tools, this architecture builds deterministic, mathematical integrity into every stage of the delivery lifecycle. Architecting this from scratch requires significant engineering overhead. Teams often accelerate the process by starting with pre-verified tools. Standardizing on Docker-hardened images, for instance, immediately provides a foundation that ships with SLSA Level 3 provenance and VEX data out of the box. The return on this investment is measured in incident response. When an upstream vulnerability drops, teams without provenance spend days in forensic scrambles. Teams with an unbroken chain run a rapid blast radius analysis, rebuild the affected artifacts, and deploy in hours. Treating the software supply chain as an engineering discipline shifts an organization's security posture. You stop relying on blind trust and start demanding definitive cryptographic proof.